Hey, so today's video is going to be on how to render projections and views of 3D images using the tnia-python library. So I'm gonna show you some utilities you can use to make some cool renderings like these ones right in your Jupyter notebooks. So if you want to get the code is in my tnia-python repository, and you can find that just by searching for it on GitHub. Should lead you right to it. And the examples I'm going to go through today are in notebooks folder, and then there's like a plotting folder, and there is several useful examples of how to render images in notebooks. Okay, so dependencies. So tnia-python is my utility library, and a lot of the videos I make, I'm using utilities from that, and I don't install set up the dependencies from the tnia-python installation, and the reason for that is this is sort of my playground, but it also is my helper library, and there's a huge number of functions in here, some related to deep learning, some related to deconvolution, some use OpenCL, some use SciPy. Some of them are based on CellPose, some TensorFlow, some PyTorch. So you can see it's a huge number of dependencies to handle all the examples. So what I usually do is the way this library is meant to be used is for every sort of like example or every set of functionality, I usually like write out what dependencies you need to run that particular example. Like for example, if I'm using it to answer a question on image SC, I'll try to include the dependency. So for this one, plotting, you need a environment with NumPy, skimage, and pyplot, plus the tnia-python library itself. And you also, if you want to do some of the interactive stuff, need to use IPY, or needs to install IPY widgets and IPyMPL. Okay, so this first example is on some static projection. So there's some really great tools out there for dynamic projections. In particular, I think Robert Hass's stack view is really, really useful, and there's a link to it in the notebook. And also, as I'm going to show in a few examples down the road in this presentation, tnia-python also has some dynamic projection tools. But I'm going to start with static projections because those are also very useful. One advantage of static projections is that they render no problem on GitHub and the web, and you can save them and keep a record of them as sort of persistent figures. Yeah, so a lot of times when you're using these dynamic projections, they're really cool because you can look at different slices and stuff like that. But when you push it to GitHub and you want to show somebody else your notebook, they sometimes the dynamic projections don't render. So static projections. First, I'm going to load a test image. This image is just Cells 3D. It's from the scikit image sample image collection. And the first thing I'm going to show, this is like the, if you're rendering using this toolkit, the best place to start, if you're like rendering a 3D image, is the show XYZ slice center. So, and I'm actually going to erase two parameters because I kind of want to show what these parameters do. So when you first start working with your data, you may not know where the objects are located. You might not know what's in it. So the first thing you might want to do is just render the center slices on each axis. And here you see XY slice, ZY slice, XZ slice, and they're all from the center. So that's just a good place to start because you don't have to figure out like which slices to, like later on when you know where everything is, you might actually want to change the slice numbers. But a good place to start is just slice center. And you don't need any parameters except the figure size. However, oftentimes when we're looking at these 3D images, especially in microscopy, the z-axis is has a larger spacing than the lateral XY axis. So the first thing you probably want to change is set the XY spacing and the Z spacing to like Actually, for this image, I don't know exactly what they are, but in microscopy, a decent first guess is 100 microns and maybe 300 in the Z. And of course, for a real project, you really want to know what they actually are when you're doing real work. But just for this little tutorial, I'm going to just estimate, yeah, like 0.1 microns and 0.3. And yeah, so there we go. That made stretched out the Z. So that in particular, that's really useful. So this image, we could sort of see what's going on even without stretching the Z. But sometimes you get images with like, I don't know, 2048 by 2048 by like 20 or something, and the Z is really like compressed and you can't really see what's happening. So sometimes even like a bigger Z than the real Z is sometimes useful to sort of see like what is happening. And like in this case, well, this is exaggerated. For this image, we don't need to do that, but you could see you could really stretch the Z if you had cases where you want to see what's going on. Okay, so the next thing I'm going to show is slice projection. For this one, we import show XYZ slice. And what we can do here is we can actually be specific about what slices we want to look at. So yeah, so in this case, I'm just going to say, hey, let's look at these slices, and then we get some crosshairs showing what we're looking at. So that's pretty informative. Another thing we can do is max projection. Max projection is really useful. Again, it's sometimes used like when we first start exploring the data. Like maybe we don't know where everything is, so we don't know. Maybe sometimes stuff isn't even at the center slices. So if we do max projection, then we can sort of see what's going on in the entire image. And then another thing we can do is sometimes if we want to like stack different figures and do comparisons, sometimes it is better just to see like the XY and the ZY and stack them like vertically, or put them side by side and do only the XY and the XZ. So yeah, so we have like variations on the functions that only do like two of the projections. And again, in this case, I look at the slice projection or the slice views and the max projection, and I could see them sort of together and sort of, see what's different between the two images. This is sort of useful if you do some processing on the image and want to look at them both. And the other thing I'll mention here is that these functions all return the actual figures. So when you want to do like any figure things, like put titles on them, yeah, you have the figure object, and you can just access the functions to put titles on them and stuff like that. So final thing I'm going to show here in the static projections is changing the color map. So yeah, so these functions all allow you to specify a color map. And yeah, so we can, sometimes you might not like the Python default color map, so you can use any of the built-in color maps. And saving figures, again, we have the figure object, so we just use like the save fig when we want to save it. Okay, so next notebook is color projections. And here I have to give some credit to Panos Oikonomu. He contributed like a really cool utility to do like these interactive slab projections. And I'm going to get to that at the end of this presentation. But what he also did is just gave like a ton of examples of how to work with colors. And I use those to implement as sort of a base to implement some more like color functionality in the notebooks. Okay, so let's open up the cells 3D, but look at this time. I think in the last one we just extracted one channel. This time we're going to keep two channels. So here's the deal with all this stuff. There's often an arbitrary number of channels, but to actually render it, you have to convert it to RGB. And even if it's 3 channels already, you may not want to use red, green, and blue as your color map. You might want to color it a little differently. So we have this create RGB function, and by default, it let's look at this. By default, it renders, it actually, when we create an RGB, sort of anti-intuitively, it doesn't color it red, green, blue. What it's actually doing is this create RGB function. You have the option of putting in like the colors you want, or a color dictionary to look up things from. But if you don't pass anything in, it's going to use this default color dictionary, which I set up, which is basically like a list of commonly used dyes that I sort of run into. And the order is kind of arbitrary, but a lot of times I get images and the DAPI channel is second. So in this case, I've got this order here, which sometimes works, but often doesn't. So often you have to specify the order. And I'll show you how to do that in a second. But anyway, these color projections, if you just don't pass anything, it uses sort of this default, and it takes your 2 or 3 or 4 or 5 or whatever color image and changes it into an RGB. And then, yeah, and then you can also, there's a little bit of things you can do. If the image is too faint, you can fool around with the display max and a couple of other things to make it enhance the contrast. And you can also sort of enhance the contrast channel by channel by changing the Vmin and Vmax, sending in like a list of them, each one corresponding to a channel when you actually do the when you actually create the RGB. So yeah, so in this example, this second example, I'm going to use I'm going to change the wave name. So I'm going to make the first one Fitzy, and of course there was a bug, so I had to stop the video. But what I did, this second parameter is actually color names. I used to call it waves, but I changed it a couple days ago. This stuff is all pretty new, so I'm still fooling. The color part is pretty new. The projections are old, but I've been tweaking the API over the last few days. So yeah, so that's basically give it a list of dye names, or you can. And I'll just emphasize here, I'm not a microscopist. I do some contract work in microscopy, so this whole idea of these dye names and how they're colored and everything, that can be definitely an area of more development and more like expert knowledge into that. But anyway, okay. So then there's also the option of specifying like just colors by names, and I think Scikit or PyPlot has a bunch of built-in names that you can use, and yeah, you could specify these colors by names, and now you see you've got a slightly different color scheme. Okay, so that is the color projections. Next thing I'm going to show are interactive. So the interactive ones are kind of neat. You get these X, Y, and Z controls, and then you could scroll into it and explore your data and find out what's in it. And then let's see here. Yeah, then there's a second. So the API for this one is tnia-plotting.interactive projections, and there's like 2 different versions. One of them, this second version is a little faster, but you have to have a notebook that supports the matplotlib widget mode. So it's implemented a little more intelligently. So it's a little faster. And then also in this notebook, there's a couple of examples of some of the code that's actually used. So if you want to make your own interactive projections, example 3 and example 4 might be kind of useful. And then example 5, again, example 5 shows how to make like a widget where you could change both frame and intensity. And for some reason, I'm getting like multiple little widgets appearing here. I'll have to investigate that. Okay, so my video is going to get cut off, but I want to make sure I get to the color max slice interactive example that Panos contributed. And this one is really cool. Let's see if I can just show you how it works before I get cut off here. Yeah, you could see the you could see, oh wow. So the interesting thing is sometimes it cuts me off at 15 minutes and sometimes it doesn't. So this is great. Maybe it knew I was showing something that was made by somebody else. So you know, with all the AI and everything these days, maybe they know what you're talking about and they know, hey, this other guy contributed something. So let's let him have a little more time to talk about somebody else's work. So anyway, yeah, this color max slice interactive example, really, really cool. You can change your X, your Y. See if I can get the whole thing in the screen here. You should see the the Y changing. It's changing slowly because the Y like thickness is pretty big right now. So I can change the Y thickness down a little bit. Change the Z. We should see the Z window changing. And then you can also do the thickness. So so right now, watch what happens. We'll change the thickness and we should see more features like appear in the Z. And I'm not sure if you can see it, but there's also there's little crosshairs showing how thick your slice is and showing where it's from. So yeah, so this visualization here is really cool and renders just right in the notebook. And again, it was created by Panos Oikonomou. Anyway, that's the video on projections, static projections in notebooks using this library. Yeah, I hope maybe you found it useful, and also if you know, if you ever think any of this stuff will be useful and you run into any problems or anything, just post on image.sc. I almost always answer questions there, like within a day at least, or if not faster. And then also, yeah, there's you can go to the GitHub site here and you can, you know, report an issue if there's anything majorly bad going on or you just have any interesting ideas. Yeah, so that's it. Thanks a lot.